using a 1 and a 3, let's make it 2 meters. It's a really big table. How fast does mass 2 need to travel to keep mass 1 from moving? All right, so first, parsing apart, what am I actually trying to find?
Is it the acceleration, the centripetal acceleration?
We'll be using that, but we're not finding that explicitly. My answer at the end is going to be what quantity?
Speed.
Yes, speed. How fast is the speed thing? So I want to find V. And we're going to solve this, first off, the force diagram. Yeah. I got my 2 masses here that I care about. I got mass 1 and mass 2. It's not chapter 2, 4, or 5, so I'm not going to do the full thing. I'm not including the ground or the table. All I really care about are those 2 masses. What are the forces acting on mass 1? That's the one that's hanging down below.
Tension.
I heard tension and more specifically? No,
Its weight.
that's the one I'm looking for. Or force due to gravity. Again, gravity, huge topic. Looking for just a small part of it. All right, so force due to gravity, otherwise known as weight, in this particular case. I got those 2 forces. I don't want M1 to move at all, and so it will be in static equilibrium. Mass 2. I got 3 forces acting on mass 2. What are they?
It's on the table.
Friction.
Oh, in reality, yes.
Sitting on the table.
But for this problem, no.
Okay. So we got some more tension. We got contact.
All right, which way is tension acting on it?
Tension is acting on it to the left. And then we got some contact on it from going down or something like that.
It's got normal force, doesn't it?
Acting which way? Because of contact, that's the contact
I
force.
was about to say, I can't never get that word right, but contact force, normal force.
Normal.
No.
And,
Normal force.
Its weight.
yep. Let's label it weight 2, since I have 2 different masses here, that's weight 1. The tensions, I'm assuming, it's a board problem. Well, of course, we're gonna make it ideal. The tension's the same. I'm not dealing with any additional forces on the string. I don't care about the mass of the string. I don't care about how the string's rubbing against the hole as mass 2 goes spiraling around. If you wish to add friction or add one of the other complications, go for it. That's not what we're doing right now, though.
Do you need to label tension as 1 and 2 as well?
At some point, we need to equate them. In reality, adding a little bit of reality to it, if we brought the rope into it, if that's 2, then there's tension 2 here, and then tension 1 there, tension 1 there. Those would have the same label, those would have the same label. So yes, if you did 1 and 2, that's fine, but in order to solve this, we need to recognize that those 2 tensions are the same in our nice ideal world.
Okay.
So I'm gonna, well, it's recorded for all posterity. So I'm not gonna get rid of that stuff. All right, so now, F equals ma. So mass 2 is going in a circle. Which one of those forces is the centripetal force?
Say that question again?
I have three forces acting on mass 2. It's traveling in a circle. Since it's traveling in a circle, there must be a centripetal force acting on it. Which one of those forces is the centripetal force?
Tension?
Tension.
Absolutely, that's the one that's pointing towards the center. So I know that the tension is equal to mass 2 times v squared over r. Or we can do the intermediate step, mass 2 times the centripetal acceleration, which is mass 2 times v squared over r. Mass 1 is in static equilibrium, so what can you tell me about those two forces acting on it?
They're equal.
I'm gonna nitpick that. I spirit of what you're saying, absolutely right, but nitpick.
Okay.
What is off when saying that the two forces are equal?
Equilibrium?
It is equilibrium, but that's not the issue.
They cancel each other out?
That's better, yeah. Why is saying that the two forces are equal is misleading?
Because they can be equal and still be affecting the object.
Say that again?
Because they can still be like equal but affecting the object to make it move.
If the forces were equal, they indeed would make it move. That's not the issue in the semantics here.
Okay.
It's a nitpick.
The tension is upwards and the weight is down.
Directions aren't the same.
Oh, okay.
All right, so the magnitudes are equal. The force up equals the force down in terms of magnitude. In other words, the tension from that has to be equal to the weight. No vector symbol over it, it's just magnitudes here. What's the formula for weight?
Energy.
Ooh, had a little bit of unison going on there. Excellent. So since the tension is equal to mg, we can actually do the numbers there. So that's 3 kilograms times, let's assume Earth, 9.8 meters per second squared. Nine point four. Feels right.
Yep, that's right.
So the tension in the string is 29.4, that's the magnitude of my centripetal force. Going to the first one there, so I have 29.4 equals mass 2, which is 1, times v squared over my radius, which is 2.
What you just said?
I'm plugging into this formula right here. I know what tension is, I just found it. And that's equal to m2 v squared over r. My mass 2 is 1 kilogram, and my radius was 2 meters. That's all I did. You have a question before we keep
Yeah, how
going?
you found out your, oh, no. I see where you got your radius from.
Okay.
Okay.
Is that a 1 in front of the v squared?
It is a 1 because the mass was 1 kilogram.
Okay.
Probably would have been nice if I picked a number other than 1, but we're here now.
You're good, mister.
I have 29, so the math problem is 29.4 over 1 is equal to v squared over 2. There are other ways of looking at it, but that's the math problem. So first, v squared. How would you solve for v squared? First step,
Multiply by 2.
okay? And so that's 58.
58.8.
Okay. And so therefore v, 7 point something.
7.67.
Meters per second.
There we go.
Second
That was
squared.
my, what are the units? Those?
What you said, meters per second?
Yes, meters
Yes,
per
so it's
second.
not squared, okay. That's-
It is meters per second.
okay.
So about 16 or 17 miles an hour that it needs to be spinning for the regular speed. And since we're here, oh, any questions on this before I ask my follow-up question? And the follow-up question is, how long does it take to actually go around the circle? Or I could word it differently, as in, what's the period of the rotation? How long does it take to go around the circle? Or how would you find it?
2 pi r
Keep going,
squared.
deviated there. What is 2 pi r?
The radius squared.
That's the circumference, right?
Okay, so 2 pi r is the distance around.
Mhm.
If once you bring r squared into it, you're now dealing with two dimensions,
Okay.
like an area. So I know that speed is distance over time. We're talking about round one, so that's 2 pi r divided by the period. So I have 7.67 is equal to 2 pi times my radius of 2 divided by t. And so t is 4 pi divided by 7.67. About 1.6.
Mm-hmm.
It's maybe 1.64.
Kilograms?
What did we just find?
Meters per second.
Speed, right now.
Oh wait, seconds, right?
Yeah,
It's the,
That's the time it takes for something to go around.
Yeah.
Seconds.
Second.
Could ask for angular speed next. Well, what the heck? Let's ask for angular speed. What's the formula for angular speed?
I don't remember.
If you did the centripetal motion lab, you would have used it. I'm willing to bet.
The angular speed.
Angular speed, yes.
I don't know, it might not be right. Said I don't know, it might not be right.
That's okay. Go for it.
I'm thinking it's like,
You want me to look before you answer, or?
yeah, I was thinking that right here.
Oh, that's a much more complicated version of what we need.
Oh, well, then, so maybe just like this,
Sort of. Anyway, what would omega be if that were the case?
this one is omega,
Oh, no, omega's the angular
or that
speed,
one, oh, so that one's velocity right there,
angular velocity.
angular velocity.
So if you solve for it, what would it be?
I don't understand the question.
If you just looked at that right there, just that, and you solve for the, I wanna get that by itself. In other words, I need to get rid of that.
Also, I'll probably, divine,
Yep.
divine,
You have to do both sides.
both sides of what?
That equals sign. If you're gonna divide it, this side, you have to divide it by that side too.
Anyone else? Well, we were all on that bit. All right, let's take a different tack. I have a formula for speed here, remember we did that whole, here's the linear terms and here are the rotational terms? The analog? What is the rotational analog of distance? Presumably it's in your notes, side by side.
Is it alpha?
No, alpha is the angular acceleration, that's the analog of A.
And theta?
What is theta? What does it represent?
Is it change in angular displacement?
Or, the words are almost there, but theta is the angle, just the angle.
No.
It's the change in the angle over the change in time. That's what, I know how long it takes to go around once. What angle does it go through if it goes around once?
360
Give me units.
degrees.
All right, or in terms of radians, because we're cool. Let me say it. Maybe not.
Is it 2 pi radians?
It is 2 pi radians. So the angular speed, that probably would have been what you used in the lab, angular speed is 2 pi radians divided by how long it took to go around that, which was 1.64. And we end up with 3.835-ish. And of course, the follow-up question is, what are the units?
Meters per second?
No, that, for angular speed, yes, angular speed, a little bit different.
Rad per second?
What'd you say?
Rad per second?
Okay, yeah, radians per second. All right. Now that the excitement in the classroom is built up to a frenzy, we need to calm down just a little bit. Why don't we take a break and regroup, we'll come back and do every person stream. We'll talk about physics. All right. Last miscellaneous topic in chapter 8. Angular momentum. Usually represented by an L. Or some unknown number. There are a couple ways, there are a couple of formulas for it. So we can just go think about linear momentum. And so, quick question, what's the formula for linear momentum? Or momentum as we called it previously?
We are gonna call that,
Is it-
mass times volume, or,
Wrong V?
velocity.
Yeah, there we go. So mass times velocity.
I said volume. I was serious too when I said that.
You know. Yes. All right, so if we're doing angular, we do the angular analogies. So what is the rotational analog of mass?
Is it just mass?
It is not just mass.
It is momentum, moment of inertia.
Moment of inertia, big I. Big I. And the rotational analog of velocity?
W, or,
Omega?
That's the one. I knew what you meant.
but so I gotta say omega?
It is an omega, not a W.
Is there any way to write it to distinguish it from just writing W?
Make it like,
My W's are straighter, like omega.
you kind of make it look like a 3 on its back.
Yeah, that's what we're looking at.
Okay.
My lowercase w is I try to put a little flare off to the side here, just to, but,
So when you're doing angular and when you're doing angular displacement, how do you differentiate those two when you're talking about it?
between angle and angular displacement?
Yes.
And displacement, remember when we were dealing with, in chapter 3, we had position, and then displacement was, we just stuck a delta in front of it. Same thing with angle is theta, change in the angle, or angular
I wanna
displacement.
apologize for asking that, that's written down right here.
Okay. No problem. And I'm pretty sure I started this thing, but it's the old, did I lock my car routine? All right, so just like momentum is conserved, angular momentum is conserved. So there's actually basically three things that are conserved: energy, momentum, and angular momentum. I remember a test in college where I was asked which of the following things are conserved. I missed it. That's one of the reasons why I'm saying it now, so that you will not miss it if you're ever asked again. Angular momentum is conserved.
And what else?
Momentum, or linear momentum,
Mm-hmm.
and energy.
Okay.
Now, there obviously are certain situations where it seems like energy is not conserved, such as if I slide a book across the table, it will stop. Energy went somewhere, but that energy went into the table. We just generally ignore that. So if I have an object, so let's say I've got oh, you know what? Let me go for it. I have a disk. Let's give it a radius of 2 meters and a mass of 4 kilograms. I got a blob sitting right there. With a mass of, make it 3 kilograms. What I